Hey guys, this is Nikhil. So in this video we will quickly go through the topic of performance of transmission lines. So this particular study, which is called as performance of lines, comes under steady state analysis. That means you perform this study under steady state condition. So what do you mean by steady state condition? Basically, simply I can say the load remains constant. If there is any load on the system, that is constant. And if load is constant, and at the same time generator side conditions also. Generator side conditions mean the speed of the generator, frequency of the generator, and voltage of the generator. So generation side also all the conditions are constant. So under these constant conditions we will study the performance of lines. So before studying the performance of lines, I want to throw light on basically what is performance. So performance for any electrical apparatus has got two indices. That means in performance analysis we will basically study about two things. So what are those two things which are generally assessed in performance is, one is called as efficiency of that particular apparatus. Okay, any apparatus it may be a transmission line, it may be a transformer, or it may be a motor or a generator. We will have to see the efficiency, and then comes the regulation. Okay, regulation. So these are the two primary indices that we will be studying in performance. So efficiency, basically we will study, there are two types of efficiency. One is called as power efficiency and another is called as energy efficiency. So in electrical engineering, power efficiency is basically taken for transmission lines and power transformers and many motors or generators, any machines, we will take the power efficiency. And coming to energy efficiency, we will specifically consider energy efficiency for a distribution transformer. That is what we take, all the efficiency of a transformer, isn't it? So that is called as energy efficiency. So what is the primary data out of efficiency is that how much is the loss, means how much input and how much output. These things already you know. So electrical transmission line, as we have seen in the last chapter, can be modeled in the form of an electrical circuit. So this electrical circuit has got an input side and there is an output side where load is connected. In between, whatever is the network or link, that is only the transmission line. So this input side is a generator and there is an output side which is a load end, and in between the link is a transmission line which can be modeled in the form of an electric circuit. And this electrical circuit of a transmission line has got a resistor, it has got an inductor, and it has got a parallel capacitor, and it has also got a parallel conductance, isn't it? This is what the transmission line model is having. So on the generator side you are sending the power, and on this side you are receiving the power. This is an AC transmission line, so you are sending active power. So PS sending active power and QS sending reactive power, and you will receive some amount of active power PR and receive some reactive power QR. So why I am specifically telling sending and receiving? Why? Because as we know, the power may get lost in between, and we have already seen which components will create this kind of losses in active power and reactive power. Active power loss is caused due to resistance and reactive power loss is caused to the line inductance, because line inductance is a consumer of reactive power. So generally if you see the active power losses in this line, now in this line, tell me where the active power has been consumed. In this resistance and this resistance, isn't it? We call this is R, this is L, this is C, and this is G, where G is the conductance of that particular resistance. So this resistance is nothing but the leakage resistance. Okay, so I can write the active power consumed by the transmission line will be equal to I square into R plus V square into G, isn't it? Assuming that this is the voltage, okay, this is the receiving sending voltage Vs and this is the receiving end voltage Vr. So I can say this power loss will be equal to I square into R into V square into G. Okay, so this particular V square by G component of loss is constant. Why? Because we operate the transmission line at a constant, whereas this component of loss is variable because it depends upon the current. So it varies with load. Okay, varies with load, whereas this is constant, but the existence of G depends upon the atmospheric condition. So basically G contributes to the leakage reactance over the insulators or the corona effect. Or I can also say this V square by G is also a representation for a corona loss. So this basically does not occur all the time. This loss does not occur all the time and it is negligible, and it will depend upon, okay, depend on atmospheric condition. Okay, that is the active power loss. And as you know, what is the reactive power loss taking place in a transmission line? So reactive power loss is nothing but I square into XL. This is the reactive power loss that is taking place in a transmission line. So generally when you take the efficiency, we only take the active power efficiency, not the reactive power efficiency. Why? Because reactive power can be generated locally. Reactive power is not a big deal, or it is not a big problem. Reactive power basically is a local problem. If you think the reactive power is not enough, connect a capacitor bank. But if you think the active power is not enough, can you connect another generator whenever you want? No, is it not possible? So management of active power is basically a global problem, we say. Why? Because it cannot be controlled locally. If there is anything that should be controlled in active power, that should be done at the generating side only, isn't it? So active power we will be considering generally as efficiency parameters. So the efficiency of a transmission line is based on active power efficiency, but not the reactive power efficiency. Please note this point. And next concept is, or next aspect is, generally the transmission line efficiency is around 90 to 95% nowadays. Okay, transmission line efficiency is 90 to 95%. That means 5 to 10% of loss is only taking place. Now you may think, sir, 90 to 95% is a very good figure. No, but no. What is the power carried by a transmission line? Hundreds of megawatts, thousands of megawatts. In 1000 megawatts, how much is 5%? How much is 5%? 50 megawatt. 50 megawatt of power you can generate how much amount of revenue? You can light how many houses, how many bills you can generate. There is a huge revenue loss for the department. Okay, even 5% loss is also not tolerable. So therefore, we are trying to increase the power transfer capacity. Okay, so that we will see in the transmission capacity concept. Okay, next concept is regulation. So what does regulation indicate? So regulation is basically two types. So regulation will be taken in two types. There will be static regulation and dynamic regulation. In static regulation, basically we will consider the voltage regulation. Okay, and we will take the voltage regulations for transmission lines, transformers, generators. That means this static regulation is only taken for such kind of apparatus whose output is electrical, whose output side is electrical, and a dynamic regulation will be taken for equipment whose output is mechanical. For example, motors. So motors will have dynamic regulation, and that example for such regulation is speed regulation. Okay, so speed regulation and dynamic regulation which will be taken for a motor, and static regulation is example voltage regulation will be taken for such devices whose electrical energy is output is electrical energy. Okay, and voltage regulation specifically specifies. So we are talking about the static equipment which is for lines, transmission line. So voltage regulation of a transmission line is given by voltage at no load. So receiving side voltage, it will be taken only for the receiving end side. So VR naught specifies the receiving end voltage at no load minus VR, where VR is the receiving end voltage at rated load or full load divided by receiving end voltage at rated load into 100. So this is the percentage voltage regulation formula. So in transmission lines also, this voltage regulation is approximately around 5 to 10%. Okay, and what is the allowable voltage regulation or allowable voltage tolerance in transmission lines? As per IE rules or international rules, 12.5% is allowable in transmission lines. Whereas on the consumer end, what is the allowable voltage toleration? Plus or minus 6% as per IE rules. So that tolerance is nothing but the allowed voltage regulation or variation in the voltage. So voltage regulation specifically states how much in the variation, how much in variation voltage is allowed in a transmission line. So this is basically what we study in performance of transmission lines. So the next concept that we have to see is classification of transmission line. Now we have understood what in the performance that we are seeing of lines. You are telling, okay, electrical lines. Now what are these lines? So we will classify these electrical lines. So as you know, basically these lines are classified as short, medium and long. So first we will see what is the basis of that particular classification. See, line is any conducting material which will carry some electrical signals of voltages and current. That can be a power transmission line, or it could be a communication like an optic fiber cable, because optic fiber cable or communication line is also carrying electrical signals, isn't it? So that is also a transmission line which is transferring for a huge distance, long distances. So basically as per IEC or international standards, we will classify the transmission line based on something called as frequency into length product, F into L product. Okay, classification of lines is based on F into L product, frequency into length product. So as per this F into L product, basically frequency units is hertz and length units is basically kilometers. So the units of this particular product is hertz kilometer. So we call such a transmission line as a short transmission line whose F into L product is up to 4000 hertz kilometer. And we call such a transmission line as medium length transmission line whose frequency length product is from 4000 hertz to 12,000 hertz kilometer to 12,000 hertz kilometer. And we call it long transmission line when the product is above 12,000 hertz kilometer. Now, what is the frequency that we use in India? Indian supply frequency is 50 hertz. So, in order to see what length of transmission lines in India will be called as short transmission line, what I will do is I will divide 4000 hertz by 50. So, if you divide 4000 by 50, what does this will give you? 80 kilometers, isn't it? So, in India, when you talk about the physical length of the line, 80 kilometers, that means up to 80 kilometers. Up to 80 kilometers length of the line, it is called as short transmission line. And simultaneously divide these ends also. The lines ranging from 80 kilometers to 240 kilometers are called as medium transmission lines. And then we are talking long transmission line, which is above 240 kilometer. 240 kilometer. Now, like this it is there. So let us take another case. What is that case is, consider there is a power communication circuit, okay, communication line. So generally communication lines operate at megahertz range. Let us assume that there is one particular transmission line, a communication line, optic fiber cable, which is operating at 1 megahertz. How much megahertz? 1 megahertz. Frequency is equal to 1 megahertz. Now, in this short transmission line, let us see in this communication line, which lines, how much length of the line is classified as short, medium, long, we will see, which is called as long transmission line. So 12,000, I will divide it by 1 megahertz. 1 megahertz means 10 power 6. So 10 power 6 means 3 zeros get cancelled over here, 3 zeros get cancelled over here. Then you will get here 10 power 3 over here. So 12 into 10 power minus 3. 12 into 10 power minus 3 kilometers, isn't it? 12 into 10 power minus 3 kilometers means that will be equal to 12 meters. 12 meters. Where is 12 meters? 12 meters is nothing but 1200 centimeters. If a line length is about 1200 centimeters, then you call it a long transmission line. If a line length is 400, less than 400 centimeters, it is short transmission line. If a line length is 400 to 1200 centimeters, it is called as medium transmission line, and for the line length above 1200, it is called as long transmission line. Now you see what is the difference. Can you tell me? Now somebody might ask you a question. I am having a transmission line which is a communication line which is of length, let us say 10 centimeters. Let us say it is some 10 centimeters. Tell me what long, is it comes under long transmission line or medium transmission lines, or let us say line of 200 centimeters, or let us call 20 meters. I am having a line of 20 meters. 20 meters means what you will think? 20 meters means less than 80 kilometers. So it should come under short transmission line. But no, bloody wrong answer. Why? Because it depends upon what? It depends upon the operating frequency. It depends upon the operating frequency, isn't it? Operating frequency is that which decides the classification of line, whether if it is long, medium or short. So there is one popular question asked in GATE examination and many PSU examinations, and many students come to me and bang their heads regarding this question. That is, see this question. What does this question says? The classification of the transmission line is based upon physical length or whatever. The answer is wavelength of the line. Why wavelength of the line? Wavelength is nothing but 1 by frequency. So basically now we have seen the classification of the line is based on frequency. That means it is indirectly based upon the wavelength of the line. Frequency is inverse of wavelength, isn't it? So the classification of a transmission line is based on the wavelength but not frequency. In the next question, for a 500 Hz excitation, 50 kilometer transmission line can be modeled as. First we will see 500 hertz means, I mean for 500 hertz, what is short transmission line, what is medium, that we will calculate. So for short transmission line, it should be less than 4000 by what is called as 500 hertz, isn't it? So this get cancelled, 4 and 8. So for a transmission line less than 8 km is called as short transmission line, and if a transmission line is between 8 kilometers to 24 kilometers, that is called as medium transmission line. For a transmission line about 24 kilometers can be called as long transmission line. Now how much is the kilometers is asking? 50 kilometer line. 50 kilometer line means which line? Long transmission line. For which frequency? For 500 hertz excitation. You might think, sir, 50 kilometers means it is short transmission line, no? But now you see, it depends upon the frequency, or I can say the wavelength of the transmission line. So now we will conclude some important points regarding this discussion. So that is classification of transmission lines. Now the transmission lines are classified as short transmission line, and a short transmission line is such a transmission line whose frequency into length product is less than 4000 hertz kilometer. Now since our Indian frequency is 50 hertz, our length of the line should be less than 80 kilometers. For transmission line operating less than 80 kilometers comes under short transmission line. We are also classify based on the voltage levels. So generally the voltage levels will be less than 20 kV. So we can also say the lines which are operating less than 20 kV voltage are also short transmission line. And what else we can discuss about short transmission line? Because the length of the transmission line is less, what we do is basically, this is a steady state analysis, we will eliminate the existence of capacitance and we will consider only, okay, the existence of R and L, resistance and inductor. Anyhow, we will not consider the existence of G, okay, only R and L is considered, and R and L are also lumped, okay. And another important aspect about short transmission line is, for protection of transmission, short transmission line, which relay is used? I hope you remember that logic which I have given to you. That is, you have to remember the order of transmission line, SML, short, medium, long, and the another word is RIM, R-I-M. So R-I-M. So okay, for short transmission line, reactance relay. For medium transmission line, impedance relay. For long transmission line, more relay. So which relay is used for short transmission line protection? We will use a reactance relay. Okay, reactance relay is used for protection of short transmission line. So likewise, we will write down for the next medium transmission line also. So medium transmission line is such transmission line whose frequency into hertz is from 4000 to 12,000 hertz kilometer, and when talking about line length, from 80 kilometers to 240 kilometers length, and voltages from 20 kV to 100 kV. And when we talk about modeling, we will consider the existence of R, L and C, and they are also in lumped fashion. And the medium transmission line is modeled in 3 different models, can be represented in 3 different models based on the placement of the capacitor. One is called as end capacitor model, and then you have nominal pi model, and then you have the last model is nominal T model. And next type of transmission line is, and the reactance relay used for medium is impedance relay. And the next line is long transmission line. So long transmission line whose frequency into length is above 12,000 hertz kilometer, and the length of the line is above 240, and voltage, operating voltage is above 100 kV. And when you talk about modeling, now the line has become lengthy. The length of the line has been increased. So if the length of the line has been increased, no more you can do this kind of approximation. Now definitely you have to consider the existence of all elements. What are the all elements? R, L, C and G. So we will consider the existence of all R, L, C, G, and we will also consider them as distributed. So but distributed, okay. So basically the practical transmission lines are, I can say, long transmission lines, and analysis of long transmission lines is very important. So basically we will analyze long transmission line in 2 states. One is called steady state analysis, and we will study in transient state analysis also. During steady state analysis, what we will do is, we will consider the existence of R, L, C, G, and we will make them lumped instead of distributed. So to make it lumped in steady state analysis, we will use a model called as equivalent pi model and equivalent T. So when compared to equivalent T, equivalent pi is more superior. So for steady state analysis of a long transmission line with all the parameters RLCG, which model do we use is equivalent pi. So basically steady state analysis of long transmission line is done by equivalent pi model. But whereas if you take for transient analysis, basically we will distribute the parameter. Transient analysis means analysis of the system under the effect of switching over voltages or lightnings or traveling surges.